Hello and welcome once again to Core Ideas, the podcast dedicated to anything and everything related to lake sediments and paleolimnology. As always, we're your hosts, myself, Adam Jeziorsky, and I'm joined, as always, by my good friend, Josh Steenpont.
Hello again, Adam.
It has been a little while.
It has been a little while. I think we said that to begin the last episode, and it's been longer since then, so we haven't improved upon, if that's a negative. Anyway, it's been a busy few weeks for everyone.
Has it been? Yeah, the world is, well, it's weird. The world is becoming more normal, even as like the headlines seem to say the opposite. It's Omicron in the headlines now, but in terms of work and semesters and stuff and entering offices, it's become a little bit harder to stick to the old schedule.
Yes, definitely. And and like we're technically still preparing for a full-on campus winter term and all that. But the podcast will continue even if it trickles along.
Yeah, at a glacial pace.
A glacial pace. How fitting. We could talk about that in a minute.
That was the goal, because
what a segue. My goodness.
A little premature, but Today's episode continues a small picture arc that we've been working on for the past couple of months now, where we've been looking at individual paleo indicators in some level of detail. And in the past, so far, we have done pollen, cladocerans, chironomids, diatoms, pups. I think that's it. And today we're going to go on 7 isotopes.
Yeah. One of those was the RSI. It was kind of still mixed in there. Yeah. I think that's it.
Yeah. And so today's topic is how stable isotopes are used in paleolimnological studies.
Sounds fun.
And something you are intimately familiar with, Josh?
Not intimately. I mean, more the theory of how stable isotopes work. It's something you talk a lot about in a bunch of teaching situations, because it's commonly used to reconstruct a lot of past environments in a range of different media, which we can talk about other things beyond lake sediments in the kind of anecdotal rambling section at the end of all of these. But not a lot of personal experiences. It's one of those things that a lot of times, if from a paleo perspective, you would send those samples away for analysis. A lot of the at least paleolimnologists I know, with a few exceptions of people who are very into isotopes, who use isotopes, do it that way.
Yeah. I have no direct experience with isotopes myself, and my closest experience have been sharing offices with people that have sent their isotope samples away.
Seen lots of talks about isotopes.
I've seen many talks. So basically, I will going to be relying on Josh a little bit here. I'll throw the questions and the softballs. Or you throw the softballs.
I hope they're very soft. Yeah.
All right.
But in terms of like background material, though, there isn't a whole deeper book on isotopes, but it does percolate through a number of different components.
Yeah. So if you're looking, you'd be looking at a couple of different chapters in part 3 of Deeper 2. So in terms of what we're going to talk about today, be chapters 13, 14, and 15 for those following along at home. That would be the chapter on inorganic carbonates, cellulose, and nitrogen.
The cellulose one is mostly about oxygen. There's some carbon stuff in there as well. So a couple that rely and talk a lot about carbon isotopes, and then a focus on nitrogen in a full chapter.
Yeah. All right. So basically, again, because we're kind of outside of our lane a little bit here, maybe we'll start at the very beginning with what are isotopes?
Are you asking me, or are you going to fill in the...
Maybe I can fill this one. No, I'm asking you.
Rhetorical. So they're examples or occurrences of an element that have different masses. So basic chemistry, high school chemistry. Elements are defined by the number of protons that they have in their nucleus, and the number of electrons can vary, and that's depends on and is important for chemical bonding and reactions and all that stuff. But they also vary in terms of the number of neutrons, which affects the variation in the overall mass of the nucleus. So the same element can have different masses based on the different number of potential neutrons that are there. And those are called isotopes, the different elemental occurrences with different masses. And the important thing that comes out is that the different mass of the nucleus of the element alter how they behave in chemical reactions in both natural chemistry but also in biology. And so that can result in variations in different areas of the environment.
Yeah. And just to illustrate this, again, this is very high school level chemistry, very fundamental stuff, but the most obvious differences are illustrated when you look at hydrogen as, quote unquote, I guess, normal hydrogen only has one proton.
Yep.
And then, but you can also have isotopes of hydrogen that either has one neutron as well or two neutrons as well. But so then H2 or deuterium would be 100% heavier per atom than normal hydrogen. And tritium or H3 would be 200% heavier. And then that is the one that you may have heard of in terms of its radioactivity.
Yeah. And that's I think that's a great example. And you said it's elemental, but it's like the basic one. But that difference in weight is so obvious. It's like 100% more. Whereas when you get to really heavy elements like lead, and the difference between like 206 and 208 atomic mass units is only 2 out of 200 and something. So it's 1% difference. And so there's much less variation.
Yeah,
so.
Much more subtle differences when you're measuring them. And so then we look at protium, deuterium, and tritium. And we also have an example there that the majority of isotope species, or like types of isotopes that can exist in the world, are unstable radioisotopes, which are part of the K series and potentially quite short-lived. And we've talked about some of these in previous episodes when that instability is useful for things like dating sediments. And so examples of that would be radioactive isotopes of carbon, lead, and cesium. However, in terms of, I guess, encountering in the wild, the vast majority of isotopes would be stable isotopes or non-radioactive isotopes, or when you're looking around in the world.
Yeah. So by and large, the bigger the difference between the number of protons and the number of neutrons, the more likely it is to be unstable or radioactive. So if there's a relatively small difference, and it will depend on the mass because that's important there, they're going to be more likely to be stable. And that's right. So the ones that we think of as sort of quote unquote normal, like carbon-12, which is the same number of neutrons as the same number as the number of protons, or oxygen-16, where there's some sort of parity between the protons and neutrons, make up the vast majority of the species, of the occurrences of those elements in nature, in all of the compounds that are made from those elements too. So the vast majority of water that you find on Earth is going to be made of the most common hydrogen isotope and the most common oxygen isotope. So it's going to be H1 and O16. But there are going to be these very rare occurrences of those other isotopes. And we know, based on the nature of them, what the relative abundance of those relatively rare things is in nature and how they behave. And that's really useful.
Yeah. And so this is a very wide field of study. So just to bring it back into paleolimnology, or I guess narrow down in terms of paleolimnology, by and large, and then of course there are exceptions to the list, But by and large, when you're throwing around the term stable isotopes and paleolimnological analyses, you're usually referring to various isotopes of carbon, oxygen, and nitrogen.
Yep. And maybe sulfur is occasionally in there, but by and large, those three, for sure.
Yeah. And those three, the various isotopic ratios, as Josh just mentioned, that are found in nature vary due to well-defined processes. And usually when you're talking about stable isotopes, you're talking about ratios and basically using what is referred to as like delta notation and referring to whether a particular sample is enriched versus depleted in the isotope of interest relative to a laboratory standard.
Yep, you can use any standard you like, but there are standards for the majority of analyses. And the delta notation, in order to use that, is the amount of the sample minus the standard over the standard multiplied by 1,000. So the units of the delta notation are in per mil, which gives you an idea of how small an amount these isotopes are in comparison to the more common isotope in the environment. So very, very small. And the numbers that you see, they'll vary, but we're talking like when you're looking at enrichment or depletion, like 10 to 15 per mil kind of values in the majority of samples that you see. So very, very small.
Okay. Yeah. And as we mentioned, the isotopic ratios have a average that you find in nature, but then because we're talking about differences in mass between individual isotopes, fractionation processes occur according to natural processes based on these weight. And the most, straightforward one of these to think of is in terms of evaporation condensation. So for example, when you're looking at condensation of water vapor as it travels inland from in an air mass, so you're coming from the ocean inland, the further inland you go, it's going to become increasingly depleted in delta 18O. Because the water molecules carrying heavier oxygen isotopes are basically going to drop out faster than the lighter ones. So you just have this general, based on the way that condensation works, the heavier stuff is going to drop out first. And so you're going to have a gradual depletion over time the further you go from the ocean.
Yep, and the evaporate will be lighter, isotopically lighter than what was left behind in the ocean as well. So you get a fractionation or a separation going on from the evaporation phase as well, because chemistry is lazy. So the O16 is going to evaporate preferentially into forming clouds, into the atmosphere to form clouds, which are then going to move over the land masses. So at each of these different steps, you end up with these separations occurring in the different isotopes based on these chemical processes. And that extends to other chemical processes too. So photosynthesis will be an important one for the carbon cycle, because obviously taking CO2 from the atmosphere, taking CO2 from carbon, not necessarily CO2, but dissolved inorganic carbon from the water in terms of aquatic organisms undergoing photosynthesis, and they'll preferentially take lighter isotopes generally to carry out their photosynthesis, which leaves behind some of the other stuff, the heavier ones like carbon-13. So all of these processes are working in this well-defined, well-understood chemical nature that results in different media, different locations in the environment having different isotope amounts.
Yeah. And then the last one on our list would be looking at nitrogen. And some of the processes you're looking at is biomagnification as you go up food chains in terms of the molecules that are fat soluble and stored, less likely to be excreted just because the chemical process involved are going to have a bias towards the lighter nitrogen containing molecules. And so that would allow you to go to distinguish between various types of animal feces, for example, in terms of the nitrogen enrichment or depletion signal that you'll find within them. And and so in terms of measuring these signals and interpreting signals in terms of a paleolimnological sense, key thing to keep in mind is that bulk analysis is usually not very viable in terms of just looking at raw sediment samples and going, okay, what is the delta? What is the oxygen, hydrogen isotope ratios within the sediment writ large? Usually you're looking at some sort of organic isolation in terms of cellulose preserved in the sediments, shells, tree rings, bubbles and ice cores that are just basically trying to isolate one physical process from all the others that may be kind of mixed up in the same sediment sample.
Yeah, the most, the broadest bulk analysis, or the most, the least refined, and I don't mean refined methodologically, I mean in terms of the sample, would be on the bulk organic matter. So that's not just taking all the sediment, because then you have the inorganic components, you have the silica compound, you have everything that's there. It's not uncommon to look at the organic carbon and then all of the organic carbon in the sample, all of the organic nitrogen in the sample, or all of the nitrogen in the sample. The carbon is more important to get that organic part mixed up. But then you can go very, very detailed and isolate individual bubbles, as Adam said, or individual diatoms, or a series of diatoms. So they can be really, really accurately measured. And that's because the masses, when you have a really clean sample with all of the same sort of material, it becomes a mass spec kind of analysis, a mass spectroscopy analysis, not unlike we talked about with POPs.
Yeah.
It's just a slightly different machine.
Yeah. And so again, you're dealing with, in the same way, in small amounts of material, and your first step is to convert your organic samples into a gas, and then you run it through the mass spec, and then individual peaks in your sample output will then be associated with particular atomic or isotopic weights.
Yeah, an isotope ratio mass spectrometer, which is used for the CNOS series, can be added in line to a elemental analyzer. So it measures the elemental composition, so the total organic carbon, or total carbon, or organic carbon if you've removed the inorganics, the total nitrogen, the total oxygen, total sulfur, whatever, and then measures it in line, like the gas carrier sends it on to the next machine. If you get to heavier isotopes, that doesn't work. It's not, it's not going to be specific enough, and you would move on to like a really sensitive ICP-MS or device like that.
Okay. So I think that's probably a good place to take a short break. We covered the background of isotopes, and we'll just take a break from one of our sponsors. Today's episode is brought to you by Field Meals Helicopter Meal Kit Service. Have you ever arrived in the field, done a hard morning of sampling, and realized you did not bring any food for your team?
You're a terrible supervisor.
Hey, we've all done it. And now there's a solution to a problem that has plagued paleolimnologists since the beginning of time. Introducing the Field Meals Helicopter Meal Kit Service. A single satellite phone call can have PB&J sandwiches delivered by helicopter to wherever your fieldwork has taken you.
But Adam, what if someone has a nut allergy?
Team members with nut allergies are no problem, as wow butter sandwiches are also available.
Delicious.
And a variety of payment methods are accepted. Credit card, PayPal, Discovery Grant or CFI account numbers, and subscription services are available.
It's peanut butter jelly time.
Anywhere, anytime. All right. So, having covered, in a very general sense, what stable isotopes are, the next step is to kind of look at what kind of questions can stable isotope records that are archived in lake sediments answer. And mainly we're definitely outside of our comfort zone here, but thought maybe we just rattle off a couple of the big ones that we have been, I guess, maybe adjacent to in our careers or sat in on a couple of conference talks for at this point.
Yep, for sure. Read about, interested in, curious about. Yeah, for sure.
Squiggly
Because there's so
lines.
many. There's lots of really interesting ones. And maybe it makes sense to go by isotope first.
Sure.
Like think about oxygen isotopes and some of the things you can do with those. For lack of a better way of organizing it.
Sounds good.
So oxygen and hydrogen, as we talked about, because they're in water molecules, and a lot of other compounds, you find hydrogen or oxygen and hydrogen together are often grouped together, and they'll be used in similar types of analyses. And they'll often look at the oxygen 18 ratio, which is the most commonly used stable isotope of oxygen, and the deuterium isotope ratio together as a way of comparing environmental changes broadly. And a lot of the uses of oxygen, hydrogen isotopes are related to water balance at the broadest level. Hydrology, tracking the movement of water, the sources of water, and the processes that result in water either building up in locations, being very evaporative, being very wet, and thinking about water balance.
Yeah. And so this is where you get into the realm of looking at lots of figures that involve the global meteoric waterline, which is the where you're looking at the enrichment depletion of both deuterium and O18 on the same graph, and then it's just a relationship that is consistent around the world. So you'd be able to plot out, because both the heavier isotopes are going to come out in a consistent rate no matter where you are in the world. So you're able to plot where you are, and that is definitely a figure I've seen many, many times, especially in the early days when I was adjacent to some like the extensive work done out of Waterloo, looking at the Peace Athabasca Delta of northern Alberta. And there,
no doubt,
had an intense interest in hydrology related to ice jam flooding, and just using the sediment records to compare the histories of closed versus open basins, so lake ponds in the landscape that were, I guess, hydrologically isolated, so basically gradually dried out over time until there was like large-scale landscape flooding, and relied on them to restore the water and then gradually evaporate down again. And looking at many of these lakes along various points on the landscape in terms of their closed versus openness, to reconstruct long-term flood histories in the region.
Yeah, and you can create those meteoric water lines more locally, not just at a global level. And so you can do that for a region, especially if you have so much information on an area like the work that's been done in the pad. You can almost use the relationship of different samples from the river environment, because it's all river flooding, to fingerprint the source of water that's getting into these lakes by looking at those ratios, and then tracking over time the evaporation as they become more evaporative, more enriched in isotopes as the evaporation gets rid of the lighter isotopes, and see how they change away from that sort of river-fed open state that Adam was talking about. So there's been so much work there, and I've been along for a little bit of that sampling on their more recent return, not that recent anymore, I guess, but more recent return trips, and that's a huge use. And then looking at it in the sediments from finding it in the cellulose, which is Brent Wolf's expertise at Laurier.
Yeah. Yeah, that's how I got my start in paleolimnology, running lots and lots of pad samples way, way back, and lots of LOIs.
Yeah, there you go. Well, you need to know the organic content in order to do that. And very different sort of questions being asked about the local hydrology and the relative proportion of flooding and water balance, but the same kind of idea. If you're thinking about using the marine isotope record in marine sediments to track long-term, like glacial cycle changes, the principles are the same. You're looking at oxygen isotope composition. You know that under certain conditions, you're going to have a greater abundance of enrichment of oxygen 18 relative to oxygen 16, and then you can track that in the sediments. And you can do that in any media. You can do it in bulk marine sediments. You can do it in the ice cores, which is basically a flip of what you would find in the marine sediment record. You can do it in corals and biologic organisms like silica. The idea is the same, is that the relative processes driving evaporation and then the return of that water back to the marine environment are going to change over understandable conditions like ice stages.
Yeah, and so it's where things like ostracods could be used in terms of climate reconstructions. And yes, there we go. Oxygen, hydrogen, isotopes, all you need to know. And this is where I bow out and you take the reins, Josh. I have now joined the ranks of listeners. I've tapped out on my isotopic knowledge at this point of the episode. So let's talk about nitrogen.
Well, there we go. Right. Okay. All right. Nothing like being put on the spot here, but that's not true. I don't believe you on that, Adam, because we know, and I'm sure you have seen many talks that have included nitrogen isotopes. Delta N15 is the most commonly used stable isotope of from a paleo perspective of nitrogen, N14 being the most common isotope. And nitrogen is an interesting one, right? Because it makes up the vast majority of our atmosphere, the gas, but it's also incredibly important in terms of a plant nutrient and the different sources of nitrogen to plants, because they can't take it from the atmosphere. They can't fix atmospheric nitrogen, are really important. So the difference between ammonia and nitrate as sources of the energy, or the nutrients for plants that they need as a way of going about their metabolism and creating their structure, can result in different signatures in the sediments and in the organism. But another really common one that I was alluding to that I'm sure you've seen talks of is using it, as you mentioned, I think in the introduction, as a tracker or a way of inferring changes in the food web structure in that environment, because of the likelihood of some of these heavier isotopes building up in greater concentrations in the tissues of organisms as they feed at higher trophic levels. So if you look at the N15 composition in the tissues of an algae versus a zooplankton versus a planktivore versus a piscivore versus the mammal at the top of the food web, you're going to get an increasing amount of that N15 as you move up that food chain. And that will be released when they excrete their waste, because a lot of waste includes a fair bit of nitrogen, and you can track that in the sediments.
Yeah. Okay, you've got me. And because we did have a guest on here not that long, I guess it is quite a while ago now, but
this year,
Matt Duda was here talking about his work on bird colonies. And so one of the proxies that he was looking at in that study was delta N15, and using the enrichment in nitrogen 15 to infer when the colonies basically were present on those isolated marine islands.
Mm-hmm. And there's so many interesting examples in the paleo literature of similar kinds of analysis. The salmon work in British Columbia and Alaska, whales in the Arctic, human influence, because we are high trophic organisms. So there's lots of really cool examples of using nitrogen as a food web indicator. Not the only thing, but I think the most, I don't know.
Yeah. Have we actually talked about the whales on the show before? With
I'm not sure we have. We've talked about the Thule whalers and the Dorset Paleo Eskimo groups.
Yeah. And just the whole which is just kind of mind blowing. And the first time I was exposed to it, of like a single whale being brought in by these paleo peoples that were whaling from like canoes, basically. And
a bowhead whale is an enormous animal.
And and just the amount of nutrients in one whale brought ashore, a couple hundred years ago, it still has
you can still see the tent ring. Yeah
of just that level of nutrient enrichment in some of these environments is kind of cool.
Yeah, and even though the baleen whales, like, they're not super high on the food web, they're not like polar bears, but they're so long lived and they eat so much that they accumulate as opposed to magnify significantly, and
they're big,
and they're such a nutrient fertilization source. So yeah, some really cool examples of nitrogen, and there are others kind of productivity related ones, but yeah, some interesting stuff.
Okay. All right, then. Okay, so you got me on nitrogen, but carbon-13 is the complicated one and the one that I really have had no exposure to so far.
Yeah. And I'll be honest, it is a complicated one. And I think people who study carbon-13 will be the first to admit that this is pretty complicated. You know, there are a lot of different processes because carbon is everywhere, right? And it's in different media. And it is, so for CO2 in the atmosphere, but all of the different carbon molecules that are, you know, sugars and food web related carbon molecules. So there's lots of different components of carbon in the environment. There's also old carbon in the environment. And so there's lots of things. All that being said, it is very common to use carbon-13, which is the most common stable isotope, as a way of thinking about the productivity of lakes and the source of nutrients. By nutrients, I mean the source of algae versus plants. So the source of the carbon in terms of where it came from, and the trophic level, and not trophic level, the organisms, I guess, that produce that. Because different photosynthetic pathways, so C3 versus C4 plants will produce different carbon isotope ratios because they have different photosynthetic processes. I assume that CAM metabolism, the sort of nighttime metabolism that plants undergo, would be different as well. But off the top of my head, I don't know. So you can track algae versus plant sources using carbon ratios. But also, as I said, I think in the introduction, that photosynthesis is relatively lazy. So it will take up more C12, which means that the remaining DIC, dissolved inorganic carbon dioxide, carbonate, bicarbonate, in the water will become enriched in C13. And any other organic matter that's then created from that water, DIC pool, will have more C13 in it. And that means that the organic matter will be enriched in C13. So you can use it as a way of tracking productivity in lakes because the algae have sucked up all the C12 and then every other use of it becomes more enriched in C13. Does that make any sense?
I think so.
Good.
Or I'll take your word for it at least. But it is definitely a broad field of study, and there are people that know much, much, much more about this than we can hope to convey in this show. But we're just highlighting it as one of the potential uses within paleo that you may.
That's right. Yep.
May be interested in if this is kind of one of your first exposures to stable isotopes as a paleo topic. And I guess the last one on our list that we didn't really go into any real detail would be talking about stable isotopes of lead, which is a completely different one, but from a paleo perspective, it'd be really used to track. I guess it's one of those things where it could have fallen a little bit into the previous episode, but tracking lead as a pollutant in terms of things like lead added to gasoline historically. Yep,
that's right. Yeah, it's more of a tracer of location. So different lead or different ore bodies and locations have different stable lead isotope ratios, and you can use those to fingerprint broadly the location of contamination in the environment from the combustion of those materials when they're put up in the air, fall down somewhere, and it's the usually 200 lead 206 208 ratio. So you look at the combination of them in order to compare them. And I'm not even sure if they use the same notation. The delta I'm not actually sure. I think you may just be looking at the ratio of those two to each other.
Okay. But the key point to note for today is that it's distinct from the lead-210 that we've been talking about in many previous episodes.
That's right. Yeah, well, but I mean, that's a good example, right? Because that is a more extreme difference, like I mentioned. So lead-210, quite relatively unstable, relatively radio decaying, and
half-life of 22 years.
Yep, that's right.
Just get into some general talk here. This isotope stuff is complicated. It's very complicated.
It really is, isn't it?
Especially, it's like, I'm going to use, a very abstract interpretation of very, very complicated overlapping chemical processes are all basically going to be distilled down into a series of squiggly lines. And I think I don't know if this is really fair to say, but I'm going to say it anyway. It's like more than many of the other paleoproxies that I have any real familiarity with. It seems more, I guess, deductive, I guess would be the word. There's more almost detective work involved once you get those signal profiles back, as opposed to, that when you're looking at something like a cladostome or a diatom profile. It's like, well, this species went up, this species went down, and you're trying to infer some just general movements within the community that may have caused them, as opposed to a more broad delta O18 got enriched here. Do we have any ideas why?
Yeah, well, absolutely. Yeah, definitely. I mean, on all of those counts, like if you picture like back to undergraduate biology and think about like picturing the drawing of the electron transport chain of photosynthesis or whatever, or any of those things, and then thinking about at each of those stages that the carbon dioxide molecule, so go back to like the early parts of photosynthesis.
Oh, this is so long ago.
It's only going to be picking the lighter, not only picking, you know what I mean? But it's more likely this is going to be happening to the lighter isotope because there's more of it, but also because of these things. That is hard to it's hard to like get your head around the chemistry of it. More so even than some of the organic pollutants, because you just assume like, okay, these are there, we made them in a lab, or they're produced by these processes. But it's at this really, really tiny level, and then it's also process related, and the processes change under different conditions. So temperature is really important for driving those, and the concentration of these things. And then on top of it, you get to the point where you're trying to interpret those data, put them into context, and there's multiple compartments in the environment that are contributing to the potential for those things to change. No doubt that it seems more complicated than there's more cyclotella now. So yeah, I agree.
And so it really, I think more than a lot of the other stuff we have talked about in previous episodes, really needs to be part of multi-proxy analyses, because, there's some, come at me if you disagree with me, but there's some element of, like, say we look at the bird colony studies, for example. If you just only looked at the delta N15 profiles, it'd be like, okay, we're seeing some enrichment 200 years ago, and then it goes down again. It's like, why? It's like, you need to know something about, well, there's a bird colony on the island now. We've got some other records that line up with current conditions. So this 200-year must also be enrichment from a similar bird colony. But the ISO profile on its own is not enough to like run with for that kind of interpretation.
For that kind of interpretation, absolutely. Yeah, I think if you're asking like big ecosystem level questions, it's a really useful tool, and it can do more than just the diatoms or just the cladocera. If you're asking about productivity in that ecosystem, in some ways, in the same way as pigments and things like that, like we'll get to talking about. But for specific questions, I think it lends itself quite nicely to incorporation with other things. It tells you things about the context in an ecosystem perspective of some of the processes linked to bioindicators or changes in other conditions that you might find. And they're very complementary in that way. But on their own, unless you're asking very specific questions, like about water balance and those kind of things, it is a little bit more big picture.
And yeah. So, this is where we kind of go. Have you ever been involved in any publications that include a global meteoritic waterline?
No, sir, I have not.
Oh, okay. Me neither.
I have published a few that may have had like delta lines, so carbon, nitrogen, never oxygen, I don't think. So no deuterium either. I've never made one of those plots with the LEL and the GMWL together. I like them. I think they're cool.
Yeah,
I think they're interesting, and I've seen them explained enough that oh, that's neat. I see what it's doing there. But no, how about you?
No,
not even as a co-author on anything.
I don't. No, I don't think so.
Oh.
Like my most, I guess, isotope adjacent period of my life would have been the work on the pad that I did years ago, but I was like a research technician at that point. I was just doing a lot of processing of samples, actually, rather than any analysis of samples. So you know what? Maybe I have to double check, but I don't think so. I don't actually remember any. But where the difference is like you've actually been to the pad, whereas I've not even done that. I've not physically been there.
4 times, 5 times, 3 times, 4 times at least. Yeah. Yeah, I have. I've been to all of those lakes that are in, were sampled in that and been back to them. I've collected little water isotope samples and obviously sediment, of course, but the water isotope samples in the little bottles. The key thing, Brent would say, is make sure there's no air in the top of it, because you don't want the air from the isotope ratio of the air getting into the water, because you want the water sample. And I think the main difference may have been that I was a postdoc at that time, and they'd also been working there for so long that when you were an undergrad technician, they were just ramping up their research, and there's always this lag effect to get material into the samples and published and know what they're talking about. And a lot of this more recent one was to return and see what had happened, so there was lots to compare to. But no, it was a cool time. It was neat to see all of these lakes and to see the difference in lakes that were very connected to the channel, basically flow through systems, versus ones that are highly, highly perched, ones that have no connection, basically air water balance, the evaporation precipitation ratio of the environment is being indicated in their sediments. And then going back and sampling them multiple times. So going in May, and then it's really, really warm, and going in June and seeing how they had changed, and then seeing that those data come out in the evaporation ratios of the lakes. Yep. It was a cool couple of years of field work.
Yeah. And so at most I've ever been isotope adjacent. I guess another isotope potential kind of source that you would have also had some exposure to was periods in your life you've been tree ring adjacent, haven't you?
Very adjacent. I mean, yes, I've been in in a lab where they have sanders and look at tree rings and that sort of thing. Yeah, yeah. And tree rings are a great record because they have their cellulose structure, and they're annually laminated, so it'd be like a varved record.
They don't move,
but they don't move. You can go back, and get a number of different individuals. You can look at dead individuals. So if you can find trees that have fallen, you can cut out the cookies from them, like a circle. And there's some interesting work on doing it in old buildings, like going into old buildings that have wood beams and timber and taking cores.
Okay.
Yeah, I'm not sure how much has been done for isotopes. There's definitely been done for dating those structures, but I would imagine isotopes too, because they're an archive of trees that are hard to find on the environment. And yeah, so it's fun. Yeah, I like tree ring stuff. It's another one of those things. Again, I've taken 1 or 2 tree cores ever, but always interested in hearing about the things that come out of them. I've never taken an ice core though.
Oh, me neither.
Partially. There's some work actually that's been done on not just ice cores, but in permafrost. So I wouldn't say I'm adjacent to that. I've never worked on it, but looking at ice wedges, because they do grow in some sort of stratigraphic manner in the permafrost, and they can be very, very old. Like there are ice wedges in the Yukon that are multiple glacial ranges. Yeah, like couple 100,000-year-old wedges.
So okay, this is where I want to plead ignorance. What do you mean by an ice wedge?
So it's like it's exactly what it looks like. It looks like a triangle inverted in the ground, and they form through freeze-thaw activity. And so the water gets into the ground, it freezes, it expands, right? Because everyone knows if you freeze a bottle of water, it gets bigger and makes a mess of your fridge or your freezer, and then water will seep down into the middle again and freeze. And so they grow a little bit at a time, and they grow from the inside out. So you get this horizontal stratigraphy of the wedge that you can go and sample.
Cool. So how physically big would one be that spans multiple glacial cycles?
4 to 5 meters.
Really? Okay.
Really big ones can be that big. The average is probably not that old. Those are exceptional examples. But a normal kind of Holocene age wedge would be as big as I am. Yeah, 6 feet tall.
Okay, that's cool. That's not something I'm familiar with at all. Cool. Learn something every day.
So there's lots of examples, lots of uses of isotopes. It's one of those techniques that spans, all of these different isotopes spans paleo-environmental media, and lakes being just one of them.
Cool. All right. Well, we hope you've enjoyed our little jaunt through stable isotopes. And I think maybe we'll be wrapping up our small picture arc here, and maybe think of something a little bit more, bounce out to like big picture going forward for a few more episodes.
See if we can knock out one more episode in 2021, and
before we have to celebrate our second anniversary.
That's right, yeah, and then I'm not sure anyone listens and actually sends in ideas, but if there's any ideas, we'll find something. If not, something a little bit more broad, and then we'll circle back to some methods again, because our list is not done yet. I think it's just maybe time for a little change for us and for you.
All right. So thanks again for listening to Core Ideas, the podcast dedicated to all things paleolimnology. If you'd like to reach out to us with a question or comment, please send us an email at coreideaspodcast@gmail.com.
Or you can contact us through Twitter at CoreIdeasPaleo, and there's only one A in paleo.
All of our past episodes and most of their corresponding show notes / blog posts can be found at our website, coreideas.ajeziorsky.ca.
And if you're so inclined, give us a rating or subscribe on Apple Podcasts, Google Play, Spotify, SoundCloud, or wherever you get your favorite podcast. Those 5-star ratings would be great, but to be honest, we really don't care. We're just doing this for fun.
Do we actually have any 5-star ratings?
I don't think we have any ratings at all.
And that's it for now. But join us again next time as we continue to explore paleolimnology in the knowledge economy era, sticking to our ethos of pure knowledge without the economy.